Now, now that we, by the way, I never finished the thought really, but when you use the solubility chart, it tells you when a solid forms. If a solid forms in a double displacement reaction, then the reaction happens. You might also have water form in a double displacement. That will be perceived as heat in the lab. That's the observation you would make. That means that reaction happens. And you might also, we're going to go over this in a little bit, but you might also have a gas. Carbon dioxide can be evolved. You'll see bubbles for that. So that's really the point of the solubility chart, is so that we can predict when chemical reactions that are double displacements can happen. For single displacements, we use something called the activity series, right? So this is just for the single displacement reactions. And basically you have this chart here, and the higher up you are, the more reactive that element is. So this says that if the element is higher than the ion, it will happen. Okay, and so in a single displacement, you have an element plus a compound, right? So in that compound is usually an ion, either a metal or a hydrogen ion, that has to be lower in the activity series, or this doesn't occur. Okay, so let's go through an example. Silver plus an acid. So acid is H plus when it reacts. And so here we look at the solubility, or sorry, the activity series, and we're looking for silver and H plus. So here's hydrogen. The ion we're interested in is H plus, and here's silver. And that would be the metal, right? So this would not react. So you can write no reaction, NR. And it would not react because the element is lower than the ion. Then our next one is, does lithium react with silver chloride? So in this scenario, lithium is the element and silver is the ion. So we got to find lithium, lithium, lithium. Oh, it's not on this one. Hold on. Okay, so this one has lithium on it. You can ignore the half reactions. We'll learn about these more in 142. These are called oxidation reactions. So the top of the activity series is the most reactive, and it turns out lithium's at the very top of this series. So if we react lithium, let's see, with silver ion, silver's definitely going to be below it. Silver is down here. So the ion is below the element. So that reaction will happen. And what that means is that the lithium becomes lithium ion. Okay. So the lithium becomes the ion, and it's going to pair up with the chlorine. And the silver becomes the element, like that. Okay. Does potassium nitrate react with lead? I wonder if you could do this on your own. Pause it and see. So potassium nitrate reacts with lead. And so our lead is the element, and probably potassium, so I'm just going to ignore the nitrate. Probably the potassium is reacting. So lead is here, and potassium's up here. So the ion is way above the element, so no reaction occurs there either. If I took Pb2 plus and potassium, the metal, that would react, right? So you would get K plus and Pb solid, right? So that's kind of how you use an activity series. It helps you to predict whether single displacement reactions are going to occur or not. I think the one tricky part to remember is that hydrogen reacts as an acid, which is hydrogen ion. Okay, it doesn't react as just H. Okay, so this is your opportunity to practice writing reactions and predicting products. So pause the video here and give it a shot. I forgot to say, while you're practicing, don't forget states of matter. So if you didn't do that, go back. Okay, so here's our answers. Okay, so The first one is a double displacement reaction. So the way to find products is first to know what type of reaction you're handling. That way, if you know it's double displacement, you just switch your cations, and then you can check the solubility rules to see what's going to be a solid and what's not. All right, and so chlorine is normally soluble, but when it's with lead, it's not, so it's going to form a solid, whereas NaNO3 is always soluble. Okay, copper does not react with acetic acid because H+ is above copper in the activity series. Calcium is above hydrogen in the activity series, so the reaction will occur. And you're going to make an element because it is a single displacement reaction. So calcium becomes the ion, and the hydrogen is the cation, so that's going to become the element, H2. We should know that hydrogen's a gas. Remember, have no fear of ice-cold beer. Ice is solid, so iodine is solid. Beer is liquid, so bromine is liquid. Everything else is a gas, including hydrogen. And then we have this one, aluminum foil, so that's a solid. Silver sulfide is actually tarnish on jewelry, so you might not have known this state, but it is a solid, and it's kind of a greenish tarnish. And it happens just over time to silver left in the air. And this is actually a pretty cool life hack from the internet. If you take aluminum foil, which is cheap, and you put your tarnished silver, whether it's jewelry or silverware or whatever, it doesn't matter, some acid, some salt, and water, and you will end up fixing your jewelry. You get quite a lot of silver ions or silver element out of that process, and the foil gets kind of tarnished and you just toss it. So kind of a neat reaction. Now this brings us to our next discussion, which is about electrolytes. And so electrolytes literally just mean, electro means conducts electricity, conducts charge, so positives and negatives, and light means to untie. So we're literally untying compounds and conducting electricity, right? And so when we say untie, we mean ionize. That is when things form ions, like they do when lead and nitrate dissolve in water. So going back to that picture from the beginning of the video. Electrolytes are an essential part of human biology, actually of all biology. Your heart, your brain, your muscles, everything runs on electrolytes being moved around. And in the human body, those electrolytes are mostly sodium, potassium, calcium, and magnesium. Okay, but they come from eating salt in our diet. Other kinds of electrolytes include acids and bases, which are another important component of our biological systems. Also, electrolytes are batteries, right? Literal batteries that you would get, for running a phone, for example. Okay, so an acid is something that tastes tart. These are just characteristics of an acid. They have a pH between 0 and 7. They turn litmus paper red. Those are the characteristics of an acid. We already know how to find acids because they always start with an H, like HCl, and they are aqueous. So acids are defined as a solution that has H+ in it. Bases contain hydroxide ions, and they are also aqueous. So we've seen some of those, like sodium hydroxide. They have a pH that's bigger than 7, well, it tops out at 14. And they taste bitter. So soap is a base, and the white part of an orange is a base. It tastes awful. It's called the pith, by the way. So the pith is full of basic compounds because insects won't eat past that point, and so it keeps the fruit protected. And so the last electrolytes are ionic compounds, which I have often referred to as salts because we do that. Ions come together to form ionic bonds. That's a salt. The caption read the wrong kind of salt. It's a salt. There we go. Okay. Anyway, so salts are ionic compounds. All three of these are the classifications that go under electrolytes. So acids are electrolytes, bases are electrolytes, and salts are electrolytes. And it means all three of those classifications of compounds form ions when you put them in water. This is an important idea, all right, because as it turns out, acids and bases always have the exact same reaction, regardless of which acid and which base you're talking about. So here's how we would write this reaction between hydrochloric acid and sodium hydroxide. You're going to do this reaction in experiment 5, so it's kind of an important one. All right, and so the important thing to know about neutralization reactions is that the H plus from the acid and the OH minus from the base are going to come together. Instead of writing HOH, we write water, H2O. So acid-base neutralizations are always going to produce water. Not always, but most of the time they produce water and a salt. Ah, good, it got me right. Here's the nitric reaction. I hope you're practicing these before you watch me do it. Same process here. These are just like our double displacements, so the cations are going to just switch places, right? So NaNO3 is our salt. That is also soluble. And water. Oh, by the way, it's a liquid. Water is our other product. Sulfuric acid is H2SO4. So this has 2 protons to lose. And so that means we got to get rid of both of these. This is 2 different H pluses, okay? It's not H2 the element. It's H plus because it's an acid. And so we are going to make our salt with potassium and sulfate. Keeping track of our charges means I need to have 2 potassiums. And I'm still going to make water. And in fact, I have to have 2 OHs and 2 Ks because I need to make 2 waters. That's because I have 2 hydrogen ions. So basically, haha, get it? We're talking about acid-base reactions, and I said basically. I'm going to let that sink in. Okay, so basically, when you have more than one hydrogen that can be reacted as an acid, you're going to produce more than one water. So if this said H3, we would produce 3 water. If it says just an H, we produce 1 water. So that's the pattern. All of them produce a salt and some number of waters. Not all acids are created equal. Some of them are stronger than others. That correlates with how much charge they can carry in an electrolyte solution. So strong electrolytes mean that if you put them in water, they will ionize completely. So every HCl you put into water forms an H plus and a Cl minus. So that means it's a strong electrolyte. It has a lot of particles, relatively speaking, that are charged, so it can carry electrons around. Anything between water here and down here is considered weak, which means they can carry an electrolyte charge, but it isn't gonna have as much energy. I like this demonstration we do in one of my intro classes where you get to put like a strong acid hooked up to a light bulb, and it lights all the way up, like as if you were plugging it in. And then you also could try a weak acid, like acetic acid, and it only lights up a little bit. You know, the filament kind of flickers in and out, and it's not as bright. That's what it means to be a weak electrolyte. I don't want you to memorize these, but there are only 6 or 7 strong acids, and they're all listed in the text. If you know those, it's very helpful to you in the future, but it's not a requirement here. Bases, OH minus and everything down is strong. So if I have NaOH or KOH or any of those, they're strong. Everything between the water on this side is also weak. And everything above that, up at the top here, means it's not a base at all. Down here means it's not an acid at all. So that's our chart. And I don't want you to memorize this. It's just to give you a sense for what it means to be strong or weak. So pause the video and go ahead and make a prediction on whether you think each of these is a strong electrolyte all ionic things are strong, and strong acids and strong bases are strong electrolytes. Weak electrolytes are weak acids and weak bases, and non-electrolytes are anything else, which is pretty much just covalent compounds. So pause the video and give it a shot. Okay, so here we go. Covalent compounds, we have 3 of them in this list. So glucose is one of them in both places. Glacial acetic acid is pure acid. It's actually not even an acid. That's a bad choice of phrases. It's pure liquid CH3COOH. It is actually not an acid because it's pure, right? We said acids had to be dissolved in water. That makes this a non-electrolyte. But if you dissolve it in water like this, then it's a weak electrolyte. Ionic things are strong. H2S falls into our weak category for acids. NH3 is a weak base. HCl is a strong base. Hopefully you got that right, but if not, keep practicing.